So we had started doing questions on Casey, and I told you that there were two types of questions that you're going to they're going to see, and one of them was that you had to uh, calculate the value of Casey. That was question number one, type number one. So in that question, what would happen was that you had initial moles that were given to you at equilibrium, right? And based on those initial moles, so for example, you have a reaction in which there's H2 and I2 reacting together, and they're at equilibrium and they're forming 2HI. So initial moles were given, and you had your equilibrium moles. For example, initially in the container, they added 0.2 moles of this, and they added 0.3 moles of this, and they added 1.2 moles of this. And then at equilibrium, you figured out that there were only 0.9 moles of HI present. So what you had to figure out the value of Kc, not only the value of Kc, you had to figure out the equilibrium moles. So initially in the container, you had 1.2 moles. Now you've got 0.9. After a certain amount of backward and forward, the reaction started going backward. Then the forward and backward reaction started. Eventually, the rate became equal. And that is when the concentration stopped changing. So the concentration of the reactants and your products is not going to be the same. Either the concentration would be lesser and greater on this side, or it would be greater on this side and lesser on this side. But the concentrations would change. So you started off with 1.2, now you've got 0.9. So that indicates that 0.3 are gone. And that indicates that 0.3 reacted. Is this clear? Because the amount of HI is now lesser. Is this clear to everyone?
Yes, sir.
So the amount of HI is lesser. So 0.3 reacted. And what did they turn into? They turned into H2 and I2. Now, according to the ratio, it's 2:1:1. So it's 0.3 reacting. That would give you how much? 0.15 are going to get produced. And 0.15 of H2 would also be produced. Is this clear? So there's going to be an extra 0.15 and 0.15 of these. TK, is this clear? Ethan, is this clear? Bhasga?
Ji, sir.
Yes, sir.
And finally, you have 0.3 moles right at the beginning and 0.15 extra getting produced. So you have 0.45 moles at equilibrium. And over here, you have you had 0.2. Now there's an extra 0.15. So the moles at equilibrium are going to be 0.35. And you can now find the value of Kc. It's going to be the concentration of HI. That's going to be squared. Divide that by the concentration of H2 and I2, which is going to be... Now, when the number of terms, whenever Kc has no units, you can use moles instead of concentration. So it's going to be 0.9 squared. And that's going to be divided by 0.35 multiplied by 0.45 to find the value of this. What are we getting?
I'm getting 5.14.
So you're getting 5.14. Just make sure you use brackets and clearly tell the calculator what's happening. So you're getting 5.14, and Kc has no units in this case. Now that was the first type of question which you had to figure out. The second type of question that you're going to get is going to be, it's going to be that Kc is known, and you're supposed to find the equilibrium concentrations. So Kc would be known, and you have to figure out the equilibrium concentration. So, for example, you have a reaction in which you have again you have H2 and I2 reacting together, and they're forming 2HI. Now, what's given is that this says 0.2 moles, this is 0.2 moles, and this is 0.5 moles. So those are some things that are already provided. Those are your initial moles, and no other information is given. The only thing that's given is that Kc has a value of 4.5. I mean, that's the only thing that's given. So how would you solve this question? How would you find the equilibrium moles? That how many moles are present at equilibrium? Now you have no idea how many moles are going to be present at equilibrium. The only thing that you can do now is that you can assume that X moles are gone. So X moles, they react. So it's just an assumption that X moles are are reacting, and they're producing HI. There's some forward reaction happening. Now X moles are going to react with X moles. It's 1:1. So X moles would react with X moles. And on the other side, it's 1:1:2. So that means 2X moles are going to be produced on this side. So if X moles are gone, X moles would be gone over here as well, and 2X moles would be produced on the other side. Is this clear?
Yes, sir.
So your moles left at equilibrium would be 0.2 initially, and then X are gone, so that's 0.2 minus X. This would also be 0.2 minus X. And on this side, you already had 0.5 moles. Now there's an extra 2X moles getting produced. So that's going to be 0.5 plus 2X. So you found your equilibrium moles in terms of X. And the only thing you can do now is you can find the expression for Kc. It's going to be HI concentration squared. It's going to be 0.5 plus 2X squared divided by the H2 concentration, 0.2 minus X, multiplied by I2 concentration, which is also 0.2 minus X. So it's going to be 0.2 minus X squared. And that's equal to 4.5. You're not supposed to solve quadratic equations, so you can underroot this. And you can underroot this side as well. If you underroot this side, the square terms are gone. And you're left with 0.5 plus 2x is equal to 0.2 times 4.5 under root, and minus x times 4.5 under root. And if I make x the subject of the equation, it's going to be 2 plus 4.5 under root. And this side would be 0.2 times 4.5 under root minus 0.5. And this whole thing gets divided by this whole thing gets divided by 4.5 under root. What do we get for x? Can you even solve this?
Sir, I'm getting negative 0.0184. 4.
Nee, that's the value of x. I said there's going to be two values of x. The other one would be that this thing over here, 4.5 under root, can have a negative value as well. So if it has a negative value, then this would become negative, and instead of 2 plus 4.5 under root, it would become 2 minus 4.5 under root. Find that value as well. So x is going to have two values.
7.62.
So you got these two values, 7.62. Anyways, one of them is wrong. You take that value, that when you try and find the equilibrium moles should come out to be equal to, they should be positive. So if you put in 0.0184 and you substitute 0.0184 into the expression, then this would be all these values over here, they're going to come out to be positive. So moles are always positive. So is this clear?
Yes.
So that's about Kc. And then you had a thing called Kp as well. So we're going to quickly do Kp and revise Kp. So we're going to do Kp now. Now Kp is the same as Kc. Uh, Not much of a difference. Both are exactly the same. They're both equilibrium constants. Now Kc was the ratio because concentration and pressure are directly proportional. But remember, the term pressure only applies to gases. That's it. Any other thing, its pressure would be constant. Because solids, their particles are tightly packed. They don't bump into the walls of the container, so they don't exert a pressure upwards or on the sides. The only pressure that they exert is due to gravity. So pressure as a term doesn't really, because solids don't have uniform pressure. Same goes for liquids. Gases are going to exert pressure equally on all sides. So it only applies to gases. And it's going to be the same thing. Like if you have a reaction and there's an N2 reacting with H2 and they're in equilibrium with 2NH3, what's going to happen is that Kp is going to be the pressure that's exerted by the products, which in this case would be NH3, and that's going to be squared, and divide that by the pressure due to N2 multiplied by the pressure due to H2, and that's going to be cubed. Is this clear?
Yes, sir.
So that is how Kp would be written. Now, for Kp, everything would be the same, except for the issue that how do you calculate pressure due to particular gases? So, for that, what you have to do is that if you have a container and you always you always measure the total pressure. The total pressure of the container is, let's say, 2 atmospheres. Then the container has all these gases. Like, for example, there's 0.15 moles of N2. In the container, there's 0.3 moles of H2. And there's 0.45 moles of NH3. Now, the container is a combination of all these gases combined. And these gases are pumping into the walls of the container and exerting this pressure. So, combined pressure is 2 atmosphere. So what you need to do is what you need to know the individual pressures. What's the pressure due to N2 alone? That's known as the partial pressure. So the formula for that is that it's the mole fraction or you can also use percentage. Like if there's 10% gas in this container, that is called N2, then the pressure that that particular gas would exert would be 10% of 2 atmospheres. So it's going to be mole fraction multiplied by the total pressure. Is this clear?
Yes, sir.
And for N2, it's going to be 0.15 divided by the total moles. And the total moles are 0.75 and zero point 0.9, right? So out of zero point 0.9, there's 0.15 moles of N2. And you're going to multiply it by 2 atmospheres. What do we get?
1/3.
So you're going to get 1/3. And similarly, we can calculate the pressure due to H2 gas. That would be 0.3 divided by zero point 0.9 multiplied by 2 atmospheres. That's 2 by 3, right? What do we get for that?
2/3.
You shouldn't. I see you're getting 2 by 3. That's fine. And what's the pressure due to NH3 now? Now, the amount of NH3 or the quantity of NH3 in the container is 0.45. That's almost half. So 0.45 divided by zero point 0.9 multiplied by, and that I think would give you 1 atmospheres.
Yes.
And all you have to do now is uh, you have to write the expression and put the values in that expression. It's going to be the partial pressure of NH3 squared, and everything would be divided by partial pressure of N2 multiplied by the partial pressure of H2, and that's going to be cubed. So it's going to be 1 squared divided by N2, which is 1 by 3, and multiplied by 2 by 3, and that's going to be cubed. Can you try and solve this?
10.13.
So we are getting 10.13, and what's the unit in this case? This one is going to be, it's atmosphere squared divided by atmosphere into atmosphere cubed. So it's going to become ATM minus 2. That's going to be our unit in this case. So is this clear?
Yes.
So just remember about mole fraction uh, or percentage. It could be both. So I'm just going to upload the KP worksheet here just one second. This one. So this one. We're going to start with the first question. These are all KP questions. So over here, The question states, and remember, you can always deal with percentage. Mole fraction is kind of percentage, so you can always deal the whole question in percentages. So he's saying that there's dinitrogen tetroxide which is 50% dissociated. So if you start off with 100, I say if you start off with 100, 50% of 100 is, or you can what you can do is you can take it as x. That you have x moles of this thing in 204. So if 50% is dissociated, so how much is gone? That means 0.5x has reacted. Half of it is gone. So you're left with how much? At equilibrium, you're left with 0.5x, right? So these are your equilibrium moles. And if 0.5x react, on the other side, how many moles would be produced? It's 1:2. So 1x would be produced. Is this clear?
Yes.
Yes.
I said
Sir,
so.
let's say I had a question.
Yes.
I mean, is this A2 physics chemistry side?
This is just the start, the revision of KC and KP. And then we're going to start. I mean, right after this, we're going to start A2.
Check.
Okay. Because you do get questions on KC and KP in A2 as well. So just a quick revision, and then you're going to start with equilibria, A2 equilibria. I say anyway. So you started off with x 50% dissociated, so you're left with 0.5x. 0.5x react, and they go to the other side, and over there it's 1:2, so 1x would be produced. So you have your moles now, and you can calculate. Remember, you can calculate the partial pressures now. It's 1 atmosphere. What's the partial pressure due to N2O4? It's going to be the mole fraction, which is 0.5 divided by the total, जो कि 1.5 बन रहा है, ठीक है, which is 1.5. The total is 1.5 moles or 1.5x moles multiplied by 1 atmosphere. So this one is going to have, that's 1/3, right? ATM.
Yes.
And this one over here is 1 divided by 1x divided by 1.5x into 1 ATM. And that is, I think, 2/3 ATM. So you have your products and you have your reactants, you have the partial pressures. So the formula of Kp in this case would be NO2 squared and divided by N2. So it's going to be 2/3 squared, and that's going to be divided by 1/3. So what do you get? I mean, it's 2.
4/3.
It's 2/3 squared divided by 1/3. So this gets cancelled out and you get 4/3 atmospheres. Similar question. Over here, you've got 20% of steam that's dissociating. So you start off with 1x, or you start off with x moles. So what's 20% of the steam had been converted into hydrogen oxygen. So 20% of this is reacting. So you're left with how much? 80%. So that's 0.8x. So that means 0.2x is taking part in the reaction. 20% is reacting. So on the other side, they're going to produce 2:2. So that's going to be 0.2 as well. And this over here would be 0.1 according to the ratio. Is that clear?
Yes, sir.
And it's again 1 ATM, so mole fraction. So what's the partial pressure of H2O? That's 0.8 divided by the total. So it's going to be 0.8 divided by 1.1 into 1. So it's going to be D. The other one would be 0.2 divided by the total moles, which is 1.1 again, and into 1. And the last one is 0.1 divided by 1.1 into 1. So you get this. Is this clear?
If you partial pressure of steam 0.8 कैसे?
20% of the steam had been converted into hydrogen oxygen. So what is left?
0.8. अच्छा,
But
0.8 is equilibrium constant.
but we assuming that it's x, okay? But we didn't know what the moles were, right? So I just took it as x.
Yeah.
So if 0.8x, so 80% is left, 20% is dissociating, right? So 0.2x is converting into the products. So you're left with
Yeah.
0.8x, which is why it's going to be D. So let's try another question where
Sir,
yes,
why is it divided by 1.1?
because what's mole fraction? Mole fraction is the moles of water divided by the
Oh,
total moles, right? Now the total moles are no longer one. I mean, you started off with 1x, right? But
yeah.
obviously, when something breaks down, you get more moles. Like one molecule, I mean, two molecules are turning into three molecules. So obviously, the number of moles would increase. So you're getting
All right.
1.1. You're getting 1.1 now. I said,
All right.
let's do another calculation. I mean, this one is easy. Easy. Just 1 second. So we have these questions that we can try. We can try this one. Uh, we're supposed to calculate the value of Kp. So you started off with 2 moles, right? So 2 moles of NO of dinitrogen tetroxide. I mean, this is dinitrogen tetroxide, which is this one actually. So not this. This is not 2 moles. The other side is 2 moles. So you started off with 2 moles and was sealed in a container. After equilibrium had been established, the total pressure was 140 kilopascal. So the whole thing had a pressure of 140 kilopascals. Now everything should be in kilopascals now. And the mixture of gases contained 1.84 moles of dinitrogen tetroxide. So at equilibrium, you have 1.84 moles of dinitrogen tetroxide, which is this one. So how many moles are missing? The number of moles have decreased now. You start off with 2. So what is it? It's 0.16 that are gone, right?
Yes.
Yes.
And what happened to those 0.16? They turn into uh, NO2, right? So it's 1:2. So over here, 0.32 extra would be produced. So at equilibrium, you're going to have 0.32 moles. Because initially you didn't have any. Now there's an extra 0.32 getting produced. So at equilibrium, you're going to have 0.32. Is this clear?
Yes, sir.
So you found your equilibrium moles. You have to write the expression for Kp, which is going to be N2O4, and the concentration of N2O4 divided by the concentration of NO2, and that's going to be squared. And calculate the yes.
Pressure. I mean, you said concentration.
Sorry, it's going to be pressure. TK, it's Kp. So everything would be pressure. Adam, why are you late? So it's going to be pressure. As anyways, calculate the number of moles of phenol. We already did that. Calculate the total number of moles of gas present at equilibrium. Hence, the mole fraction of each gas is basically in the next part. Is basically looking for calculating Kp. Calculate the partial pressures. Calculate the value of the equilibrium constant Kp. So we're going to do all of that in one step. Like what's the pressure due to what's the pressure due to the different gases? Due to N2O4, what's the partial pressure? It's going to be 1.84 moles divided by the total moles, which are what? 1.84 plus 0.32. What do you get for that? 2.16?
Yes.
So it's 2.16 multiplied by 140 kilopascals. And the partial pressure due to this gas is going to be 0.32. The total moles are 2.16. And it's going to be multiplied by 140. And then you're going to put these values in your expression for Kp, which is, in this particular case, Kp is going to be what? It's going to be N2O4 squared. No, in the N2O4 power 1. So it's going to be 1.84 divided by 2.16. And that's multiplied by 140 kilopascals. And this thing divided by, can you even calculate this and tell me what the values are? What do we get for this?
119260.
So 1 pascals or kilopascals?
Pascals.
Pascals.
You don't have to convert it into pascals. Like whatever answer that you're going to get, the unit is now kilopascals for this. So just multiply it by 140.
119.
Kitna 11?
9.3.
So that's the pressure in kilopascals. So it's 119.3 kilopascals. What about the other side? The numerator.
20.7.
So that's coming out to be 20 point.
So
And this one is going to be squared. Based on what the equation looks like. It's 2NO2, so the coefficient is going to become the exponent. So what's our value of Kp?
0.277.
So you're getting 0.277. Now,
sir, ये कौन सा step है? I mean, why did you divide both the pressures?
both the pressures with what? I mean, this
you
thing?
divided one. जी.
That's Kp. Well, what's the expression for Kp?
Pressure of.
I mean, it's the pressure of the product divided by the pressure of the
Yeah, ठीक है.
reactants, ठीक है? So that is what Kp is. I said then you have I mean, we did this one. You can go through a few more questions. Most of the questions are going to be straightforward. You just have to find the value of Kp. So try calculating the whole of it. Try calculating this one. Do this as homework. Figure out the value of Kp. This is from the contact process. It's this reaction. Maybe they didn't give you the reaction. So it's SO2 with O2 in equilibrium with SO3. So try and do this question. So tomorrow we're going to start with A2 equilibria. Okay, just a second. I'm sending you the question. ठीक है साकिब मुझे आप 10 o'clock ना रिमाइंड कराओ ठीक है चल let's continue tomorrow we'll start with A2 equilibria. This was just a short quick revision for AS. Okay then, take care.
चलो, okay. Thank you.
Thank you.